In Chapter 8, we're going to learn about elimination reactions. Now, for a brief preview of what to expect in this coming chapter, we're actually going to see that most substitution reactions are accompanied by competing elimination reactions. And these elimination reactions make alkenes. So oftentimes you can take a substrate that has a good leaving group and you can react it with a nucleophile. And we're going to see that depending on the reaction conditions, you can get one of two products, either substitution or elimination. So let's take a look at how that process happens. Well, we start off with a substrate with a good leaving group. Now, most substrates have carbons attached to the carbon with the leaving group. And these are referred to as a vicinal carbon, or sometimes it's referred to as a beta carbon. If the carbon with the leaving group is the alpha carbon, then any carbon attached to that alpha carbon is designated as a beta carbon or a vicinal carbon. And notice that in this particular example, the vicinal carbon, that beta carbon, has a hydrogen attached to it. So what can happen? Well, we're going to see that when you have a nucleophile that approaches this substrate with the leaving group, one of two things can happen. Either what we've seen in the previous chapter, you simply replace the leaving group with the nucleophile, and hence you get a substitution reaction. In this chapter, though, we're going to focus on a different pathway in which the nucleophile can essentially remove a beta or a vicinal hydrogen. And in this process, what happens is the electrons from the carbon-hydrogen bond form a pi bond, and the leaving group comes off. So the leaving group is still coming off in this situation, but now the nucleophile is acting as essentially a Bronsted base. Where we get H and U, right? So the nucleophile has removed a proton, and this is what is referred to as elimination. Now, the idea is that elimination reactions result in the formation of a double bond, a pi bond, after deprotonation and loss of a leaving group from a vicinal carbon. So deprotonation from a vicinal carbon and loss of the leaving group from that alpha carbon. And what we're going to see is that there are two primary kinds of elimination reactions. There's E1 and there's E2. Just like there was SN1 and SN2, there's E1 and E2. And we're going to see that E1 reactions, like SN1 reactions, involve carbocations. And because of this, at the end of the chapter, we're going to actually discuss something that perplexes many students, and that is that carbocations can undergo rearrangement. And when carbocations undergo rearrangement, you get different products from what you originally expected. So we're going to explore kind of that at the very end of the chapter. So these are some of the concepts that you want to consider as you're studying. The first is, how do elimination reactions differ from substitution reactions? Is there a way that we can, quantify an elimination reaction is going to occur, or a substitution reaction is going to occur, or maybe both of them are going to occur? And if so, what conditions promote E1 versus E2 versus SN1 versus SN2? So, how can we kind of fine-tune a particular reaction to follow one pathway over the other three? And then lastly, how does stereospecificity differ between E1 and E2? And so these are some of the things that we're going to talk about. Of course, there's going to be other concepts to consider, such as regioselectivity. And so we have regioselectivity, stereoselectivity, or specificity, and we're going to explore all of these things in this chapter. And hopefully, by the end of this chapter, you'll have a very good understanding of number one, equilibrium, and number two, that a reaction can follow more than one pathway. And it's simply a matter of trying to find conditions to satisfy one particular pathway over the other so that you can maximize product yield of the particular product that you're actually after.